UM400A. This microscope is automated. It has a motorized X-ray stage, autofocus, and also it can rotate nose piece automatically. We like to build a chamber or miniature incubator to put on top of the stage. Look at the samples from top, while we like to control temperature, CO2, and humidity. One of the samples we like to work on, it will be a 35mm petri dish. If we can do more than one, it will be great. It will be a couple of challenges here. Let's review together. One of the challenge here is the working distance, the height of sample, and also the available distance from top of stage when it is at the lowest position up to the edge of objective lens. So if we move the stage at the lowest position and measure it up to the edge of 10x objective lens, we have maximum 35mm. So using an off-the-shelf chamber will not work. So we have to make a custom chamber. Another challenge here is basically the scanning area. So as I said, this microscope is automated and it was designed particularly for glasses slide scanning. So if we move this in X and Y direction, the maximum area we can cover with this, it will be the full size of a double size glasses slide. So in X direction or horizontally, we can go up to 80mm, which is just bigger than a glasses slide size, which is 75mm or 3 inches. And also in the Y direction or depth, basically this can go up to, as I said, as double size glasses slide, which will be 40mm. So basically, since we have a 40 by 80mm scanning area, we are hoping to be able to collect the images of two 35mm petri dishes. Let's see what we can do. So we decided to use a thermoplate metal piece, so it fits on top of the stage. So there are a couple of challenges here. So first of all, we have to protect this hitting plate, give enough gap or space between the hot plate of here and the stage. Otherwise, you can't get the stable temperature. So we use this spacer here. The second thing is, and similarly from the back, so it doesn't touch the stage. So we use the benefit of these two screws here, which moves in the X direction, and we can connect simply right there. And also this is smooth enough, which moves in X direction, while in the Y direction this already moves. So if you're going to use this for a short term and you don't need to control any humidity or CO2, this plate itself will be sufficient, and we just need to put either just simply a petri dish on top of that, or maybe some sample holders such as this. But if you're going to control the temperature and run this experiment for long term, it will be some challenges. So there is one insert here, basically if you need to use a transmitter light, so we can remove this piece and we can get the benefit of that. Otherwise we close this because we like to control the humidity, and also we don't like to lose the temperature. So we measured and we did a couple of calculations. We come up with this design. So the height, basically it will be matter. If you are going to close this, it shouldn't be higher, and if it is short, then it won't be enough for humidity control. So inside this, basically this will be our scanning area, 40 by 80mm. It can be a single petri dish sitting at the center or two petri dishes. And for that one, basically we use either single insert such as this. It fits right here, and that will be the case. Okay, or it can be two inserts of petri dish, one right here and second one right here. Okay, so but if you're going to collect the image with the closed lid, there will be some challenges. First of all, it will be condensation issue. Second, we don't like to capture the image from top because we will lose the image quality, and we don't like using the plastic in the light path. So if we remove this, we will lose the humidity. The second question is, how are we going to control humidity? So we can close the system and insert a humidified air from the side. But once we do that, the second problem is, if you're going to close this, let's say we add a lid here, then we will have a condensation issue. So we add the lid, and then we saw there are some drops. So what we decided to do is basically, and also keep in mind that if we put the lid over there, capturing the image from top, still it has to go through that glass or plexiglass. So what can we do? So over here we have installed that miniature incubator on this stage, and this moves, as you can see, perfectly in X direction and also in Y direction. So if I go closer to the objective lens edge, we can see basically we can scan the whole area of these two petri dishes. So if we are going to have a closed system, basically once we cover this, it will be condensation issue because we are injecting the humidified air. So the first thing we did, we add the thermoplate for the humidified air, and we increase that. We still see the condensation, so that doesn't help. The second thing is, we try to do, it will be using a heated glass at top, such as this. So this helps, particularly if we keep the lid warm, it will avoid condensation. It will be another issue. First, we can get the image of the bacteria culture or any gel or anything from the surface of that sample, because we have a limited working distance of this objective lens, particularly over 10x. So even if you increase the height of your gel, you lift the sample, there will be another issue. The main issue is, since we are using this heated glass, this has some coatings, and you will see some garbage image is coming because of that coating to your images. If you are doing a p-fluorescence imaging, that will be absolutely a big issue. Even in the bright field, you can easily grab that. So what can we do? So we decided to remove this lid as is and use a special lid. And in this case, basically the goal is to reach inside the cell culture. So we made a hole inside that hot heated glass. So the size over there, as you can see, it is tight enough, the lens goes inside. This solves those issues we discussed earlier, but it adds two more issues. One, since the objective lens is below this warm glass, still you will have condensation at the edge of objective lens. To solve that issue, we come up with the objective lens warmer, or using this jacket, warm jacket, so we keep the objective lens warm. The second thing, and the most important part, as I said earlier, this is an automated XY stage. So if we are going to do this into scan area, we are not going to capture just a single spot. particularly we don't know where our spot is, so then we can make the hole for that. So what we did, we keep this one floating. So basically the goal is, so as you can see here, this moves, but it keeps sealed. The stage moves, the top lid stays there. This moves fair enough. And then the size is basically designed in a way that if even this rotates for some reasons, it keeps closed from all corners of the chamber. The problem is solved. So in brief, we have a closed miniature incubator or chamber with the controlled temperature, humidity, CO2, and also which allows us scanning a big area inside the chamber with the direct access to the surface of a gel or any culture or any living organism over there. So we have a controller for the metal plate. We control the temperature for the top part. We also control the temperature for the humidified air, its flow as well as another thermoplate to keep the objective lens warm, and all of these basically avoids condensation issue. This allows capturing the images for at least 40 by 80 millimeters scanning area. Over here we added a special reflected illumination system to this microscope, and we are able to capture the images in bright field, dark field, reflected mood, as well as transmitted mood if we need so, plus epifluorescent imaging. Hopefully this helps you to get an idea about upright automated biological or industrial microscope with a closed miniature incubator with the controlled parameters.